Hi folks. Today we're going to talk about the Poisson distribution, which is quite useful in, well, we're going to apply it first to queuing theory, which will be the next topic, but it's also quite useful in computer simulations, and it's a good way to model events that can happen at random moments in time or at random places in space. Okay. So I'm going to begin by reviewing the binomial distribution. I assume you've seen this before. If you haven't, you can ask me about it during office hours. I'd be happy to talk about it. But this is, it's basically the distribution of the number of heads you get when you flip a coin n times. Right? So the way this works is you flip a coin n times, right? And p is equal to the probability of getting heads each time. So this may not be a fair coin, right? The probability of getting heads is p, and that may not be equal to 1/2, right? So it could be a bias coin. And then the capital letter X represents the number of heads that came up during all n flips, right? So you flip a coin maybe 8 times, you might get 5 heads, right? And then X would be equal to 8. X is a random variable, that's why it's denoted by a capital letter to distinguish it from an ordinary variable. So a random variable is just a variable whose value depends on a random process. Okay, so the probability of getting a certain number of heads when you flip a coin n times. By the way, in the context here, what we're talking about more generally, this is called a Bernoulli process, where you take the same simple trial, very simple experiment, so to speak, where you flip for example, when you flip a coin, and there's only 2 outcomes, right? That's called a Bernoulli trial, and a Bernoulli process is when you repeat Bernoulli trials over and over again, n times, and then just count the number of successes that you got. So in general, for any Bernoulli process, as long as the trial is exactly the same each time, the same probability of success, and all the trials are independent of one another, then it's called the Bernoulli process, and you can compute the probabilities using the formula I'm about to give you. So this here says that the probability that the actual number of successes that you got, if there's only 2 outcomes, you can call one of them success and the other one failure. Again, that's just the general terminology. We can refer to success or failure. In the case of flipping a coin, we can say heads or tails, though, of course. So the probability of getting R successes when you flip the coin n times, or R heads when you flip the coin n times, that's what this says. P stands for probability. X is the number of successes you actually got, and R is some fixed number. So we're saying, what's the probability if the actual number of successes we got happens to be equal to R? Well, the basic idea of the formula is that you take P to the R. That is basically the probability that you get R successes in a row. P times P times P times P R times. 1 minus P to the n minus R, that's the probability that you get n minus R failures in a row, right? The probability of a failure would be 1 minus P, and that would happen n minus R times. But that's only one way you could get R successes, because the R successes and the n minus R failures could come in any order. So you also have to multiply by the choose function, which represents how many different orders you can rearrange those successes and failures in. So recall that n choose R is n factorial over R factorial times n minus R factorial. Right? That's the formula for the choose function. Okay, so this is the formula for the probability of getting a certain number of successes in a Bernoulli process. This is the formula for the mean. This is pretty much common sense, right? If you perform n trials, and on each trial you have probability p of success, then you figure that fraction p of the number of trials n will be successes. So you figure on average you're going to get n times p, or p times n successes. Right? And the formula for the variance is actually pretty simple. We just multiply by an extra factor of 1 minus p. Okay, so, and again, if you want to ask about any of that, feel free to bring it up in office hours. I can say more about the binomial distribution and Bernoulli processes. But I want to apply it now to deriving the formulas for the Poisson distribution. So the idea of a Poisson distribution is that you let n go to infinity, right? So you let the number of trials approach infinity, or actually reach infinity. You think about the limit, but you take the limit while keeping mu fixed. We want mu to be fixed. Now remember, mu is n times p, so we can ensure that mu is fixed as n goes to infinity by setting p equal to mu over n. Right? If p is equal to mu over n, then the mean n times p will be fixed at mu. Right? So in the process of taking this limit, we're going to, in principle, we're looking at a whole sequence of binomial distributions as n goes to infinity. But for all those distributions, the mu will be the same. It'll be a fixed value. But n will be going to infinity and p will be going to 0. Right? So the idea is we want to model a process in which there are an infinite number of trials at which a success could occur, but success becomes increasingly rare, right? Because the probability of success is approaching 0. So successes are so rare that we actually change the language here. Instead of talking about successes, we talk about events. So if at one of these infinitely many trials success occurs, we call that an event. And if a failure occurs, that's a non-event, because that's pretty much what we expect to happen, because the probability of success is essentially 0. So okay, so we've got an infinite number of trials. Success or events could occur at any one of those trials, but events are so rare that we only expect a finite number of them to happen. In fact, on average, only mu events will happen, even when there are infinitely many trials in which they could occur. So one natural way to think about this is you could imagine a process that occurs in time. So imagine that this blue line here at the bottom is the time axis, and the red dots are events that can happen at any moment in time, right? So at any moment on this timeline, an event could happen. In this particular case, only 8 events actually happen, right? The random variable x is equal to the number of events that actually occurred. In this case that I've sketched, it's equal to 8. But in principle, an event could happen at any point in time, but only finitely many will ever happen because the probability of success is so low for an individual event. And so you can imagine this representing, for example, points in time at which a customer walks into a store, right? Walks through the front door of a store. And this is the reason it's important for queuing theory. We will use this Poisson distribution to model the process of customers entering a store at random moments. But you can actually use it for all sorts of processes that occur in space or in time. And I'll talk about that on the next slide. Okay, so I just mentioned already that one of the things you can use the Poisson process for is to model customers entering a store. But there are lots of things you could model natural disasters like earthquakes and tornadoes, which seem to happen more or less at random points in time. Although I should caution that technically independence of events is probably violated here. I mean, if for example, if the weather conditions are favorable for tornadoes on one day, they're likely to be more favorable than not for tornadoes the next day as well, right? So in this case, the fact that a tornado occurs on a particular day probably makes it more likely that there'll be a tornado on the next day. So strictly speaking, the trials are not really independent of one another, right? However, you could nevertheless try to model tornadoes that way. Maybe you could, rather than doing it for days, maybe you could do it for weeks in which a tornado occurs, probably less dependence between tornadoes in different weeks and different days. Also, same thing applies to earthquakes, for example. Probably if the geological conditions favor an earthquake occurring, then they'll probably continue for some time, right? So if, and like for example, if an earthquake occurs, that it's typically followed in the short term by a number of aftershocks, right? So the probability of earthquakes goes up in the immediate aftermath of an earthquake. On the other hand, maybe if there's a major earthquake, it relieves the stress in the rock layers, and then the probability of an earthquake in the medium term goes down. I don't know. I don't know very much about earthquakes, but that seems plausible. Another example of applications of the Poisson distribution would be hits at a website, right? You figure people are randomly dialing up a website. You know, hits can happen at any moment, and those are pretty random. Those events are pretty independent of one another, because people might be hitting a website from any place in the world, right? And there's no real necessary connection between one person hitting a website and somebody else doing it. Calls to a helpline. You get the idea. There are all sorts of applications for of the Poisson process to events that happen in time. So in principle, whenever you have events that can happen at any moment in time, but you know you expect only finitely many of these events, and furthermore, we assume that the moments in time are all independent of one another. So just because you had an event at one particular moment in time doesn't mean you're more likely to get it the next moment or moments soon after. Okay, but you can also use this to model events in space, right, or things that could happen at different points in space. So one example I often see here is points of infection in a petri dish. So you can have cultures of bacteria or something growing in a petri dish. You get copying errors in computer memory, right, which seem to happen more or less at random. Again, I don't know whether independence might be violated in that case, but I'm guessing it's pretty random. Flaws in a picture, so that would be like a two-dimensional structure where you could have glitches in either a digital image, or you could have actual flaws or chips in a physical picture. You could have atomic decay. You could have a block of uranium or something where particles decay at random places, right? And so those are all things as well that you can model using the Poisson distribution. So it's quite versatile in that respect. You can use it for both space and time. Before we get into the I'm going to compute exactly the formulas for the Poisson distribution, but let's kind of think about what we expect to occur. So one thing we expect is that the probability of an event at any particular point is 0, right? As we said, we're going to model this by letting the probability of a success in an individual trial approach 0. So we would expect that however a calculation works out, the probability of an event at a particular point is 0. And that kind of implies that the probability of two events occurring at the same time is 0. Right? Because we only expect there to be finitely many events, and if we've got finitely many events, and the probability of the second event occurring at any one of finitely many particular points in time where an event has already occurred, that's also going to be 0. We would also expect, maybe a little less obvious, but we would expect that the sum of two independent Poisson random variables would also be Poisson. So for example, if the blue box down here represents one Poisson process where events could happen at any point in the blue box, right? And let's say that x is a random variable which has the Poisson distribution with mean mu, right? So this is the notation we use. We say x is Poisson with parameter mu. And let's say in the green box we have another process going on, the random variable y represents the number of events that occur in the green box, and y is Poisson with parameter nu, right? So they have different means. But if you add up x plus y, then that's basically, it's going to behave like a Poisson random variable. That the combination of blue box and green box are going to behave kind of like just a larger Poisson process with a bigger mean. Now we would expect the average number of events to be mu plus nu, but apart from that, we would expect it to behave like a typical Poisson distribution. So we'd like to verify all these things after we do our calculation. Okay, so let's do the calculation. First, let me review a few key facts from calculus that you've had. I think you've all seen the power series expression for the exponential function, right? The e to the x is 1 plus x squared over 2 plus x cubed over 3 factorial, etc. Right? And in particular, the only application I'm going to make of that now is that when x is very small, right, if x happens to be a very small number, right, as I'm saying here, then all of these, or most of these terms are going to be second order, right? If x is small, then x squared is even smaller, and x cubed is smaller still. So these are all higher order, which means they're of a lower order of magnitude terms than x itself. And therefore, we can argue that therefore that we can neglect those terms because they're so small, and therefore we would expect that when x is very small, e to the x would be approximately equal to just 1 plus x. Right? I mean, for example, if x is 0, can't get smaller than that, then e to the 0 is in fact just equal to 1, so that's correct. But in fact, it works for any small value of x. As long as x is close to 0, then e to the x is approximately 1 plus x. In particular, that means that, well, look at this term here. Remember, this term occurred in the Bernoulli formula for the binomial distribution. 1 minus p times, or rather raised to the n minus r. Well, if x happens to be equal to minus p, then we can apply this approximation here. So let me say that. So if x is equal to 1 minus p, then we can apply that approximation, and we can say that therefore 1 minus p to the n minus r, well, 1 minus p is approximately e to the minus p. Now, n minus r, I'm going to say, is approximately just equal to n, for the reason that r is a fixed number. So for if we're calculating the probability of r successes, we're thinking of r as being a fixed number, but we're letting n, the number of trials, go to infinity. So only n is going to infinity. P is going to 0, of course, so that's what justifies using this approximation. But r is fixed, so n minus r, as n goes to infinity, you know, for a large n, n minus r is practically the same as n. So therefore, we can approximate this term in the limit, right, as n goes to infinity and p goes to 0, we can approximate it as simply e to the minus np. Okay, so that's one thing that will help us. The other thing we'll need is we'll need an approximation for this one of the other factors in the Bernoulli formula, n choose r. Now, n choose r, as I said, it's n factorial over r factorial times n minus r factorial. Another way you can write it is you write out the factors of n, well, the factors starting with n times n minus 1 times n minus 2 down to n minus r plus 1. In other words, we write out the whole number starting at n and decreasing by 1, and we write out r of those factors, right? So there are r factors starting at n. And we divide by r factorial. Now, once again, if n is going to infinity and r is a fixed number, then n minus r plus 1 is not going to be significantly different from n when n is very large, right? Subtracting r from an extremely large number is not going to make much difference. So basically, we could approximate the numerator by saying we've just got r factors of n, so that's n to the r. And therefore, the n choose r, we can approximate as n to the r over r factorial. Okay, now let's write out the Bernoulli formula again. So the Bernoulli formula is here, and we throw in our approximation. So n choose r is n to the r over r factorial. I'm just copying over, let me try to call this here, let me see, I'm just going to copy over the p to the r, and then the 1 minus p to the n minus r is approximated that way, right? So we've approximated each factor in the expression. And when you simplify this and do some canceling, oh yeah, let me just point out that, recall that n times p is equal to mu, right? So when we multiply n to the r times p to the r, that's n times p to the r, so that's mu to the r, right? In addition, this np, that's also mu, so I've written, this should be a minus, all right, I gotta go back and fix that. But this e to the minus, that should be e to the minus mu, and divided by r factorial. So we get this formula. In the limit, as the number of trials goes to 0 while the mean stays fixed at mu, the probability of r events is equal to mu to the r over r factorial times e to the minus mu. Okay, so that's the formula that we came up with. Now, of course, we did some estimating and taking the limit. We should really verify that this is now a valid probability distribution, right? And what does that mean? Well, we just have to check that the probabilities are all non-negative, which is obvious, right? That's pretty obvious. But we should also check that these numbers here actually add up to 1, right? Because probabilities do have to add up to 1. So that turns out to be easy to do, because if you sum up all those probabilities from r goes to 0 to infinity, all the possible values of r, well, factor out the e to the minus mu, right? Pull that out front, and what you've got here is, again, you've got this series, power series for e to the x, right? That's basically the power series for e to the x written in sigma notation. So you've got e to the minus mu times the sigma expression is e to the mu, and that comes out to be 1. So it worked out beautifully. The sum of all these probabilities is 1. They're all non-negative. So this is certainly a valid probability distribution, right? And next, we'd kind of like to see if it has the properties that we'd like it to have. Okay, now let's verify that that formula that we came up with for the Poisson distribution gives us the mean that we wanted. Remember, we wanted the mean to be mu, right? So we set up the construction so that as the limit the limit of n goes to infinity, mu would be fixed, right? So therefore, we would hope and expect that the mean of the resulting Poisson distribution would also be mu. So let's just verify that. It's easy to do. Remember, the definition of the way you can calculate expected value is kind of the definition is that you take the sum of r times the probability of r, right? And you take the sum over all r values, which in our case goes from 0 to infinity. So I'm just using the formula for the probability we calculated on the previous page. And if you rearrange things a little bit, let's see, so what I did here was I took the e to the minus mu and I pulled that out. I also pulled out one factor of mu. I pulled one factor of mu out, but I left the other r minus 1 factors inside. And then when you do that, well, let's see. When r is 0, of course, that's the initial value of the summation. When r is 0, then this term actually disappears, right? So we can kind of ignore the case when r equals 0. We can start the sum at 1. And therefore, I'm just rewriting it that way. Sum goes from 1 to infinity. But starting the sum at 1 and now having r minus 1 in place of r in the sum end means that this sum end is actually equivalent to the original one. It's really the same thing as just the original sum of as r goes from 0 to infinity of mu to the r over r factorial. And that, of course, is just e to the mu. So therefore, this whole sum here, this whole sum here just reduces to e to the mu. And therefore, we've got mu times e to the minus mu times e to the mu. The last two factors cancel, and the result is that the mean is, in fact, mu, as desired. Okay, so that's good. We can calculate the variance in a similar way there are various ways of calculating the variance. What I'm going to use is what's called the, I'm going to compute the factorial moment. This guy here, in probability theory, this is known as the factorial moment. So there are different kinds of moments. There are first moments, which is the mean, and the second moment, right, which is the expected value of x squared. The factorial moment is the expected value of x times x minus 1, because this looks like the start of a factorial expression, right, x times x minus 1. And sometimes computing the factorial moment is more convenient for calculating the variance than is computing the second moment, right? So this is one of those cases. So we actually compute the factorial moment, that is the expected value of x times x minus 1. So as usual, when you're computing expected value, you just multiply the value times the probability that that value occurs, right? So for each value of r, we multiply the value of x times x minus 1, which would be r minus 1, times the probability that we worked out on the previous page. Again, you rearrange things in a very similar way. Here I took out two factors of mu, and I also took out the factor of e to the minus mu. And then in a similar way, what you get is you get a displaced version of the summation for the exponential function, right? So once again, we get e to the minus mu times e to the mu canceling. And in this case, the expected value comes out to be mu squared. Now, the question is, how does this relate to the variance? Well, first of all, the second moment we can now compute easily. The second moment is the expected value of x squared. And we just computed the expected value of x times x minus 1. So that's the expected value of x squared minus the expected value of x. So if we just add in the expected value of x, we'll get the second moment. So we get mu squared from the calculation we just did, plus mu for the expected value of x that we did previously. So the second moment is mu squared plus mu, and finally the variance is the second moment minus the square of the first moment. And so it comes out to be just mu. So that's kind of nice. It makes it very easy to remember this. The mean and the variance of the Poisson distribution are both equal to mu. Okay, that's nice and simple. One other thing I mentioned earlier is we kind of expect that if you have two independent Poisson random variables, right, x and y are completely independent Poisson processes, they're from independent Poisson processes, and we add them together, then x plus y should also be a Poisson random variable, and the mean of x plus y should just be the mean of x plus the mean of y. So you can check this. I don't think I'll go through the details here. I'll leave it for you if you're interested. I should say that this result is pretty intuitively obvious, that in fact the result is that the sum of x plus y is in fact a new Poisson random variable with parameter, or with mean mu plus nu. You can check the algebra pretty easily. It's pretty straightforward. You just say, how do you compute the probability that z equals k, where z is equal to x plus y? Well, there are a number of ways that z could be equal to k. Basically, any combination of x and y values that sum up to k would make z equal to k. So we simply sum up over all those possible combinations of x and y values whose sum is equal to k, right? So therefore, we compute the probability in each case, which is, because the x and y are independent, we just multiply their individual probabilities. You substitute in their formulas from the Poisson distribution, right? The formula for x and the formula for y. You rearrange terms a bit. In particular, you can bring out the e to the mu and the e to the nu. We can bring those out. We can combine the I factorial and the k minus I factorial. And also notice that I introduce a new factor of k factorial. So I put one in the numerator inside the sum and in the denominator outside the sum. So I haven't actually changed anything. But now this is basically equal to the binomial formula for the sum of a binomial power, right? That the mu plus nu to the k is equal to this guy, this sum, right? This is n choose or k choose I, right? So what we've got here is k choose I times mu to the I times nu to the k minus I. And this is exactly the formula for this expression, for mu plus nu raised to the k, the binomial formula, binomial expansion that you learned in high school, probably. Okay, and then once you got that, we can see that now this formula is exactly in the same form as the formula for the probabilities of a Poisson random variable. So this establishes that z is in fact a Poisson random variable where the parameter, or the mean, is mu plus nu. Okay, so that's nice to be able to confirm that. Finally, one other thing that we will find useful is to do a little more examination of this Poisson process. Right? Sometimes we imagine that we've got a Poisson process that is ongoing, but we may temporarily want to focus only on one section of the entire process. So, for example, if you've got if you're modeling customers entering the store over the course of a day, right? You can imagine you have customers entering during a whole, I don't know, 8 or 12-hour period, right, during the course of the day. But for a particular application, you might just want to focus on maybe a 5-minute period or a 1-hour period or something. So you might want to focus on just a fraction of the entire period. Well, it's easy to do that with Poisson processes because a fraction of a Poisson process behaves like a Poisson process with a fraction of the mean, right? It just means that you still have a Poisson process, but the expected value is going to be small, right? So to make this quantitative, let's say, suppose we have, and for concreteness, I'll assume this is a timed Poisson process. So we've got a Poisson process occurring in time, but you know, it applies in space too. But suppose you have a timed Poisson process with mean mu. And suppose, however, we don't want to count the number of events in the entire process, but just in the first half of the time, right? So we'll let x be equal to the number of events that occur in just the first half of that time period. Well, we would expect in the first half of that time period that the average number of events would just be mu over 2, right? So if you expect mu events in the entire time period, then you'd expect mu over 2 events in the first half of the time period, and therefore you would expect that x would be a random variable whose distribution is Poisson with mean mu over 2. So in general, if you're just looking at a fraction q of the total time, right, of the total time period, then you can just assume that that has a Poisson distribution, and all you have to do is adjust the mean to be q times mu, right? If q is the fraction of the time you're looking at, then the mean would also be q times the original mean. Right? Now, so first of all, that just shows it's very easy to scale up and down the time, or the space, if you're talking about a spatial Poisson process. You can very easily scale up the time or space just by multiplying by mu, right? Scaling up mu correspondingly. But another nice thing about this is we can actually get another interpretation of this parameter mu, right? We say mu is the average number of events in this particular amount of time, but there's another interpretation we can give it, and we get that by examining what happens as this fraction q goes to 0. So suppose we take smaller and smaller fractions of the original time period, then what happens? Well, again, I'm just going to write out the formula for the probability, right? That formula we got for the Poisson probabilities, and I'm going to use the approximation I mentioned before, but here I'm using it in the opposite direction. Earlier I pointed out that for example, e to the minus q, if q is small, then minus q mu, that's a mu, not a u, minus q mu would be also very small, and therefore this would be approximately 1 minus q mu. Right? And I'm using that here, so I'm saying e to the minus q mu is approximately equal to 1 minus q mu. Okay, so I'm making that change. And now look at what happens when we apply this formula for various values of r, and assuming that q is infinitesimally small, whatever that means. But, you know, it's vanishingly small. Well, when r is 0, then of course this term would just go out, right, if r is 0. And therefore the probability would, and also r factorial would also be 1. So therefore the whole probability would reduce to simply 1 minus q mu. And because q is very small, this is essentially 1, right? This is as close to, makes no difference to 1. And so we could say that in a very small time period, it's almost certain that the number of events would be 0, right? So if you look at an infinitesimally small time period, we can be almost certain there'll be no events. When r is 1, however, in that case you get, let's see, in that case this, what did I not put? Oh, here we go. In that case, this term here just becomes q mu. We've got 1 minus q mu. R factorial is just 1 factorial, so that disappears. Now, we get this expression, q mu times 1 minus q mu. Now, here's the thing. If you were to expand that, of course, what you would get would be q mu minus q mu squared. And because q mu is vanishingly small, this is a second-order term. It's a vanishingly small term squared, so it's orders of magnitude even smaller, or at least one order of magnitude even smaller. And so we can basically ignore that, and we can say that this probability is essentially equal to q mu. Right? Now, we could say this is possible. It's very small, but it's possible. Okay, so it's possible that you could have one event in a infinitesimally small time interval, but it's very unlikely. Finally, if r is bigger than 1, then this factor is a higher order infinitesimal, right? The q mu is vanishingly close to 0. We're raising it to the rth power. So there's no way to rescue that. That is just 0, right? And we can say in that case it's basically impossible. So first of all, I'll point out that this confirms a suspicion we had earlier, that it's basically impossible for two events to happen at once. When you look at an infinitesimal time interval, it's basically impossible for more than one event to happen. Okay, so that's basically impossible. So in an infinitesimal time interval, almost certainly there'll be no events. It's possible there'll be one event, but it's rather unlikely. Okay, let me just re-express this result in a slightly different way. If you're going to be changing the time interval for a Poisson process, then it's most convenient to specify mu to be the mean number of events per unit time, right? The mean number of events per 1 second or 1 day, whatever your unit of time is. And that just makes it easier to scale things up, right? And if mu is the number of events per unit time, and then q is just a fraction of unit time, so it's just a small amount of time, right? It's just an infinitesimal time interval. So we can think of it, in this case, q is just dt. It's just an infinitesimal time interval. So if I replace the formulas previously, if I just replace q by dt, then what we see is that in an infinitesimal time interval, so basically we're looking at like a time interval from t to t plus dt, right? This little infinitesimal time interval like that, then the probability of no events is basically 1 minus mu dt, right? I've taken this formula and I replaced q by dt. The probability of one event is mu dt, and the probability of more than one event is basically 0. So this fact here in particular suggests that mu represents the probability density of events. So if you had like M365, you did some probability theory, you probably talked about probability density, so that's the rate at which probability increases as you expand the time period, right, or the parameter, right? So you can talk about the probability density function, for example, for an interval, well, for say the normal distribution, and any particular value that the normal random variable might take is equal to 0, but the probability for an interval is non-zero, right? So we say the probability density is the rate at which the probability increases as you increase the length of the interval. And so that's kind of what mu represents. It represents the probability density of events occurring in this Poisson process. It's the density per unit time of the Poisson process. And that'll actually be useful for some applications later. So we're going to talk about the exponential distribution. Maybe even we'll touch on the gamma distribution. So this way of looking at the Poisson process will be quite useful.